One moment while the YouTube goes live. All right. So it is live on YouTube. Let's wait for this train to go. Get started. This is January 4th, 2021. The topic for today is explainable machine learning. In particular, because this is a deep learning workshop, we'll pay a lot of attention to interpretability and explainability of deep learning models. Now, when we build machine learning models, whether it's deep learning or not, people have often believed that there is a trade-off between explainability or interpretability and the performance of a model. So you often find graphs that look something like this. So let me get the topic here, explainable. Machine learning. So people often make a graph that sort of looks like this. And this is the performance of a model, and this is its interpretability, or let's say human interpretability. How easily can you explain it to a person what those models are? So if you think about it, some models are very, very interpretable. For example, a decision tree, a linear classifier, for example, if you look at logistic classifier, it is reasonably performing, but highly interpretable. So this would be logistic. Let me just look at classifiers for a moment. Regression are very, very interpretable. Somewhere here is a decision tree, let's say. It has a slightly better performance and not just one decision boundary, but it has quite a few splits and whatnot. So I would say that it belongs somewhere here, a decision tree. And then once you move away from the simple models and you go to, for example, either kernel methods or to ensemble methods. So examples of the ensemble learning would be, would somebody like to give me an example?
Random trees.
Random forest, yes, and gradient boosting methods, XGBoost and whatnot, CAT-boost, etc., etc. All of these, they use an ensemble or a collection of models. If you take them in random forest as decision trees. So when you take a whole collection of these trees and you average their prediction, for example, in bagging a random forest, then it is very hard to explain what is happening at a given point and why that point was considered. Let's say if you're trying to distinguish between a cat and a dog, why this thing, this particular data point is attributed to a cat, for example. right? Let's say that you have the weight and size of a cat. Interpretability becomes hard. So what happens is you see a general trend like this. You get the ensemble methods, random forest, boosting, XGBoost, etc. There are many of these. And so all of these, you realize that what you lose is interpretability. Along the same line, you have similar situation you have for kernel methods, kernel methods, SVM, etc. What happens is they create actually very simple models, but they make a very straight hyperplane as a decision boundary. But they do it in a very high dimensional space, and that dimensional space is sometimes infinite dimensional. For example, if you take the Gaussian kernel, we are projecting data into a Hilbert space, which inherently is infinite dimension. So to say that I have a linear decision boundary in an infinite dimensional space is not terribly useful to a common man on the street in being able to understand what exactly is the implication of each of these factors in, let's say, you take a real life situation. If you're trying to determine whether or not in 5 years you'll develop diabetes based on your weight and your habits and so on and so forth and your hereditary, if you just come up with a prediction, the question that will come is, how did you come up with the prediction? What should I do? Right? Uh, will I get more effect or benefit by exercising? Will I get more benefit by cutting down on portion sizes? Would I get more? I mean, what are the factors that will have the most benefit? And models like these, they have a difficult time giving you an explanation of why it's said whether or not you'll have diabetes, let us say, in 5 years. Right? So interpretability is important, and like with support vector machines, to say that in an infinite dimensional Hilbert space there is a decision boundary. If you are on one side of it, then you will have, and the other side not, means nothing to a common person. Likewise, for ensemble methods, like, let's say random forest and XGBoost, etc., there's always this thing that how did you come up with this understanding? What is the real dynamics between the factors and the response? Right? So for example, if you think of machine learning as the way that we have been thinking about it, X vector goes in, right? There is some function such that you get the y hat. So in other words, y hat is some function of the X vector up to an error term. If you think of machine learning like this, the question is, what is F? How easy is it to understand F? Right? That is a crucial problem. When you are talking about logistic regression, let's say logistic regression, F is very easy to understand. Fx is equal to 1 plus e to the, this is minus, I hope I got this one right. Yeah, so this is your logistic equation, right? Or another way to, so this is the way you make a prediction on whether it's a cat or a dog as a probability. This is the understandable equation. It draws a very straight decision boundary. Let's say that this region is cat, this region is dog, right? And this is your decision boundary. While this equation looks complicated, it actually, the real thing is just a line, which is w dot x. Right? This line is the equation of the line, a straight linear equation for the decision boundary. And so it's highly interpretable. Linear regression is, of course, very directly just w dot x, right? With a bias term, which I have included into the weight, into the x vector itself. So those are highly interpretable models. But once you do a random forest or any of these ensembles, now the question is, what is X? What is F, rather, right? And did you even explicitly analytically compute it? Is there an analytical expression for it? And the answer there becomes that no, it is, we didn't even try to. We just went and subdivided the regions in a decision tree based on whether there are more cats in this region or there are more dogs in this region, and so forth. So you remember the algorithms for decision tree and what we were up to. So it becomes hard to answer this question, what is F? And that is the heart of explaining the explanation, right? So as you move to deep learning, the situation becomes even worse, because what happens in deep learning is, so suppose you have a deep learning model, let's say deep learning, whatever input goes in here, it goes through, let's say, arbitrary many nodes. Each of the nodes applies it with weight. Now, this part is Z1. Let me just call it Z1, Z2, Z3. They will produce Z4, Zn. And they will all do their weight 1.x, weight 2.x, and so forth. They will all do weight n dot x, the weight associated with this vector here. But that is not enough, because this thing, each node, also does the second part that it does is it applies an activation function to it, right? A nonlinear, this goes into a nonlinear activation function. Do you remember, guys, a sigmoid function? So sigma is the activation function. Yeah, let me write it here. Sigma is the activation function. And it could be your ReLU, the simplest. It could be your sigmoid. It could be your logistic. It could be your tanh, and so on and so forth. So each of these are nonlinear functions. They create a nonlinear distortion. And if you remember early on in this course, we talked about it, that the whole point is you need these distortions to be able to create a universal approximator. A neural network as a universal approximator that can approximate any arbitrary function f, you do need distortions. So you have these distortions. Now this distortion goes into the second layer and it gets further distorted. And you can imagine that as you go and keep mashing it up, mashing the input, as it goes from layer to layer and goes through more and more nonlinear distortion, you can quite a bit see that it's very hard to keep track of what's happening to X. Are we following, guys? All we remember at the end is that there are certain scores that come out. And if it is a classification problem, you do a softmax of it. And you pick out that it happens to be a cat. Right? The most activated, the bulb that lit up the most was the cat rather than the dog. Right? So in other words, deep learning leads to highly nonlinear models. You can't explain it. So the problem with this is you can't say that because in deep learning, let us say that it's not always true, but quite often if you're dealing with unstructured data like audio and video, it turns out that quite often the deep learning model would be like this. It would give you high performance or accuracy and opaque. These are opaque models. Sorry, I apologize for this spelling. Opaque. These are opaque models. In other words, low interpretability, low. Does this make sense, guys? Very low interpretability. But then that has a potential for problem because of many, many things. Like, for example, yesterday we talked about it. Fundamental questions of bias come into this. If the data has bias, your model will learn biases and you won't know. that it has biases. So one story that sort of circulates in the AI community quite a bit, and I've never really found out whether it's true or not, but it certainly has a message to it. The story goes as follows: that at some point the military approached Silicon Valley outfit, AI outfit, and said, can you distinguish between civilian vehicles and military vehicles? And if I were to pose this problem to you, you would say, well, that seems like a simple problem of image classification. Sure enough, we can do it if we get enough data. So the military, well, obligingly brought boxes and boxes of pictures. Now, how did it get pictures? It asked the soldiers to go take lots of snaps of civilian vehicles and military vehicles. The whole point is that if you target a vehicle, you don't want to target a civilian vehicle. You want to, obviously, if you suspect enemy combatants, you probably want to target a military vehicle or some such justification. So the company trained the neural net uh, to that problem. And as you can imagine, today neural nets are extraordinarily smart. They will train almost easily, very easily, to be able to tell those things apart with very high accuracy. So in the lab, the accuracy was very high. When the model was actually deployed in the field, though, for mysterious reasons, it was a complete disaster. Right? Now people began to ask, why is that? Was there overfitting? But then it couldn't be because the military tested it out with new pictures that the startup didn't have access to, or the company didn't have access to. It seemed to work just fine in the lab, even on the test data set. And yet in the field, it failed. And as the story goes, the reason for that was an inherent bias in the data, which of course the deep learning model couldn't explain because it's a black box. And the inherent bias was that soldiers see military vehicles typically in their base camp in the mornings and evenings before they go out for their tour of duty and after they come back from their tour of duty. So if you ask them to take lots of pictures of military vehicles, they'll just take it early in the morning before going on their tour or before going out, or late in the day when they get back all the vehicles. And when do you find civilian vehicles? You'll find it in broad daylight, right? So you're on a beat, you're touring a certain route, and all around you are civilian vehicles. So you keep lots of pictures, and it is broad daylight. And so what the neural network presumably picked up on was ambient light conditions. The the daylight pictures, all of them, it was marking as civilian, and the pictures that were in this sort of low light conditions, it was marking as military, but you wouldn't know that about the bias. So that story speaks to how, or sort of is a cautionary tale about the dangers of using black box models. Now, well, that's a story. We do know that there are some very real situations that have happened. We know that, for example, people tried to create algorithmic hiring. Many companies did that. One of them, Amazon, actually got sued because it was discriminating, I believe, against women and against races or blacks or something like that. So, US protected classes. And when people looked into it, why it was doing it, well, the model was very accurate, apparently. It did as well as what the human interviewers were doing. But when you look back at the data, it turns out that the human interviewers were biased, presumably, and that bias was perpetuated in the algorithm, except that in the human case, I suppose nobody questioned it. In the case of AI, people were suspicious and they questioned it. And because they questioned it, it turned out that the flaw was in the data itself. And so the bias of the data gets perpetuated in the models you build. That's a problem. The other problem is just the sheer interpretability. For example, if a model is going to, let's take the example of there was a model that claimed it could predict how often you would be, how likely you were as a criminal to recommit a crime or something like that, or whether or not you should be let out on bail. Right? The idea being that they will let you out on bail if you are a good citizen now, reformed citizen. On the other hand, if there's a high probability that you'll commit a crime again, and then people are hesitant to let you out on bail. And from what I understand, one company created a software which people started using. Now, there was a lot of confidence in that black box, except that till somebody pointed out that this model is not even accurate. It's a black box and it's not even accurate. The predictions that it makes are not better than you pick random people off the street and ask them to make a prediction about a person, whether he's likely to commit the crime or not. And it has about the same accuracy. So that also speaks of the danger that we might uh, get caught up in the hype and start believing that machine learning or AI models are somehow magical, and they can solve the problems when they really can't. So the question therefore comes, you really need to look into the box and see what really is going on. And such stories go on and on. There was a facial recognition system created, I believe, by um, I think, yeah, this Amazon itself. Again, so they wanted to give it to law enforcement, and it would tell what a person is or whatever. And people were using it, and I suppose the company was promoting it quite a bit. Till some researchers thankfully noticed and did a simple experiment. They fed the faces of all the US congressmen and senators, the Black Caucus. And it turned out that for all these senators and congressmen who were black, in quite often it would identify them not as the sort of highly law-abiding citizens that they were, but instead would mark them as rapists and serial killers and whatnot, murderers and all sorts of nasty things. It would identify them as, and that set the alarms going because it seemed to do extremely poorly with Afro-American faces. Right? And then when you look at these systems, the explanations are very easy. You can quite imagine people like us, engineers sitting in our offices, and we need some data to train the AI. What do? We start taking pictures of each of us in the office. And when you do that, the demographics that you are able to work well with is the demographic of people on these campuses. It is an unfortunate thing that on those campuses there is a scarcity of Afro-American people and other minorities. And because of that, well, your model is simply not trained to deal with it. And it seems to do a terrible job of it. So well, maybe an explanation, I don't know, right? Sort of. So these things do go on in the field. Again, it speaks to the fact that you can't trust an AI model. You have to ask it to explain itself. But then the question arises, how do you make a model explain itself? Like when you have a black box model, how do you get it to explain itself? Right? That is a fundamental question. You have a deep neural network, many layers deep. Nowadays, people are going like hundreds of layers deep. Right? At that level, what does it mean to have interpretation in the model or asking the model to explain itself? If you look from a technical perspective, you may say, well, the cause is lost. And that is what a lot of people believed, and even today believe. They seem to see sort of a rough inverse relationship, something like this. They seem to see a relationship that goes like this, that says that the more the power of a model is in predicting, the worse it will be, the more likely it is to be a black box. And a lot of people said that, it's a fact of life, just accept it. Right? When you're driving a car, for example, and it's a self-driven car, perhaps you don't care so much for interpretability there, though one can argue there too it matters. But certainly there are a few situations where it may not matter. The only thing that matters is it drives correctly. But in most situations, you do want an explanation of why the model is making the predictions it is making. Right? And so a lot of inquiry has gone into this field, and this has become now a very active area of research. It is being investigated along many completely independent directions or orthogonal axes. And it is hard to keep track. The amount of research here is so much that it is rather hard to keep track of it. So I will be posting for you uh, uh, a couple of review papers from archive where some researchers have created what they called a starters or a field guide through all the landscape of uh, research that is being done on model interpretability or explanations, explainable AI. Now, it's a broad area, and most people are probably not aware that this area of research has already been bearing fruits to the extent that today, just as when you build a model, you validate the model, you do its predictions, you make plots. In the same way, you should actually, one more step you should add, you should make the model explain itself, right? And that is the topic for today. How does a model go about explaining its details, even if it is a black box model? So we'll learn a few techniques. I will start with two techniques, which are, uh, actually three different directions. Two of them are agnostic. In other words, they don't care whether it's a deep neural network or whether it is random forest or whatever it is. They will give you an answer no matter what. Then, uh, then, then we'll do another set of approaches, three, four approaches, which are very, very particular to deep neural networks. Okay? So before I start, would anybody like to ask a question? You guys are all very quiet.
So, Asif, a quick question.
Mhm.
Um, what is the state of art? Is it agnostic models that are ruling, or particular models that are, explainable models that are tuned to those particular architecture that are? What is the direction of the research, uh, the current state of the art?
At this moment, research is rapidly moving forward in all directions. Some researchers are very focused on creating model agnostic explainable algorithms, explanation algorithms. And many researchers are looking at it algorithm by algorithm. So, for example, there is a huge body of research that only focuses on deep neural networks.
I see. I
Right?
see.
And it is a little hard to say. Like, I can tell you what I do from personal experience. Right?
Mhm.
See, uh, suppose I'm doing tabular data, right? For me, it is a given that I would do three things. I would do the Shapley, I would do line, and
Mhm.
I would do something called PDP, partial dependency plots, right? It
Fine.
is almost second nature. It's part of my routine to do things like that. Because to me, that is part of, just like you have, you do, I told you that when you get data, if you remember in these workshops, you need to become friends with the data, right? Even before you build a model, understand the data. What is it, right? In the same way, I've always felt that once you build a model, it is all right that your model is making good predictions, but now you need to make friends with the model because that model is going to be deployed to production. It will affect the real world in tangible ways. So it is important that something that you're going to unleash on the world, you understand it. And so having these things, having these things ready and explain, give you intuition into it is important. One more reason that is important is you can catch mistakes. If your model is latching on to wrong things and giving importance to the wrong features or wrong combinations, you will catch it. You will know that something is wrong here in the model. And so it is important to do that. Also, just seeing how, okay, so we'll talk about this, the line, the Shapley, and so forth, and the PDPs today. When it is deep learning, if I'm doing image processing and so forth, where pretty much deep learning reigns, what do I do there? A lot of people believe actually that you can't use Shapely or Line, but actually you can. I do use it there also. But and PTP is also partial dependency plot. But what I do, and it's very interesting actually, they are able to show in a picture what to pay attention to. But more than that, we use deep learning techniques as its own special things, and those techniques I will talk about. Right? Today. Those are pretty powerful techniques. One by one, I'll introduce them to you.
And
And
Asif, there is one more thing that I again come back to it. I couldn't understand is additive nature of these explainable models. It depends on the additive nature of the features, and some claim that may not be the case, and that's why Shapely is dependent on additive nature to explain its feature importance. So that's what they mean by additive nature, and I don't know if I'm explaining it rightly, but something I couldn't get past. I would really appreciate.
that, that is a good question. So there has always been this question that, see, whenever you make generalized additive models, right, that how valid it is. It turns out that actually you can make additive models with considerable validity. It goes to the basic fact of mathematics that you can do simple Taylor's expansion of any function. So there is truth to it. The only thing is you can't make a globally additive model. Those additivities are local,
I
right? Yeah, and the reason, I mean, I have heard those debates and I almost feel like explaining to them basic mathematics or calculus. Right? So within a local region, you do have additivity because in a local, we'll talk about it actually. Why don't you hold that question in your mind?
Yeah,
Because
I really have this very deep. I mean, this is I don't understand it deeply, but I would really, because I'm using it in my work, I need to explain it in terms. I would really appreciate your help.
yes, I'll do that. And in fact, the way I'll explain it is non-standard. See, most of the literature in this is written by, I don't know, programmers and people who write it in, or mathematicians who have couched it in very abstract language. I'm going to talk in terms of geometry, just as much of machine learning we learned as geometry, right? So I'll give you a very simple geometric intuition, and I believe it will remove all such um, questions. It will make it easy to answer all such questions that you have.
Thanks.
Are we together? All right. So with those words, I would like to get started. Give me a moment. Where is my water, guys? Give me a moment, guys. Huh? I need to go get myself a glass of water. Yes. So, all right. That is one question. Is there anything else that you guys want me to focus on and talk about? I do know that some of you have already taken my workshop, the boot camp last year. So I took you through some of these exercises that we will do on Wednesday. Some of these, not all of these, because we did not cover deep learning. Now, how many of you have here been through Shapley and Line and partial dependency plots? Let me see. Anil, Praveen, you too, and Nisarg, you also, isn't it? And Pradeep,
Yes, sir.
and Kate.
Yeah.
Oh, so quite a few of you. And Sudhir, you too. Were you there in the boot camp?
Yeah, 100% yes.
Yes, yes, you were there, right. So a pretty sizable part of the audience, at least 1/3 of you, have been through. So when did I go into the theory of Shapley and Lime in those time, or did we just do the practical? Do you guys remember?
You went through the theory.
I did go through the theory. Okay, it's good. So for you guys, it may be a review. If you want, you can take a walk and come back in an hour. So with that in place, let me, I have a whole set of topics that I wanted to discuss. Okay, let me start with a very simple geometric explanation of things. And pay attention to the geometry that is it, right? Thank you. geometric perspective. See, remember I said that in a way, when you write y is some function of x, right? What are we saying? If it is regression, let's take the case of regression. Let me generalize these ideas step by step so you see it. For if in 1D, in one dimension, y, what you're saying is y hat is some curve. If this is x, this is y. You just don't know what curve it is. Are we together, guys? A function is nothing but a curve. Are we together? Do give me some feedback so I know.
Yeah.
This is very straightforward, right?
Mhm.
Now, furthermore, let us just impose because if you make smooth and continuous curves of this thing, then this is regression. Right? In 1D, what is classification? It could be again this curve, except that this is a decision boundary. This is the regression curve. And the same thing for classification. This happens to be the decision boundary. Right? But whether it is, and so these are yellow points, let's say, on this side, and let's say that these are some other class, right? The pink class or red class, whatever it is, red triangles class, let's say, are sitting here in this part of the feature space, right? And so and the way you would look at classification is that you have two features, x1, x2 here, and this is the decision boundary that you're searching for, right? Now, let us generalize it to higher dimensions. So in higher dimensions, what happens? What happens is that this becomes, let's say that you have this. Let me just give the intuition in 2 dimensions for regression. What will happen? This will become a surface, right? Some form of a surface. Are we together? Your regression surface, it's a regression surface, right? So for any point, x1, x2, let's say, here, this is x1, let's say this is x2. What you have is, you have some value here, which is your y hat. This is y hat, x1, x2, for x1, x2. In the base manifold, right? So these surfaces, mathematicians often call manifold. And remember, I've been using this word manifold. Now, manifold has a more formal definition, but simply put, if you remember what I said is, a manifold is a bed sheet. A bed sheet. A bed sheet, right, essentially. And a bed sheet can be crumpled and whatnot, and it can take all sorts of peculiar shape. Sort of like that. But it has the following properties. It is obviously, let's have a bedsheet without tears, no tears, or discontinuities. It is smooth, right? So it is not an iron bedsheet with creases or something, sharp edges. It is smooth everywhere. The word people use is differentiable. It's differentiable. So what we are looking at, and it has one property, which is very crucial to manifolds, which is that locally, in the eyes of an ant, or God forbid, bedbug, crawling somewhere on the sheet, what happens? The world looks how? It's very tiny. The bug is very, very tiny, or a bed bug is so tiny you can barely see it, right? A dust mite or whatever it is. Now, for that bed sheet looks what? It will look flat. Locally, it looks flat, isn't it? So imagine just imagine a sphere. If you take only a local patch, you realize that if you make this patch small, very small patch, it will look flat. Would you agree? If on a sphere, you take a very, very small patch of the sphere, then to a little bug, to a little ant, it will look flat.
Yes.
Right? And in fact, this is history. We are the ants living on the big sphere of Earth, tiny little creatures. And for the longest time, what did we believe? That the world is flat, the Earth is flat, isn't it? We wouldn't believe that the Earth could be a sphere or spherical in shape. And that again speaks to the kind of surfaces we are looking at. The surface of the Earth is a perfectly good manifold in some sense, right? Concept of a manifold. So locally, it looks flat. Now, so what does it mean? If it locally looks flat, you can put IE is Euclidean. Euclidean means you can just put Euclidean axis, x1, x2 locally, right? You can make, let's say that it's two-dimensional sphere. The surface of the Earth is an example. You can put a little this thing, coordinates there, and measure things with respect to any arbitrary origin. You can say, for example, this is a very real fact. I don't know if it is true in the US or not, but in India, there is a concept of 0 mile. Have you heard of that concept? Every city has a 0 mile. It is the reference point or the origin. I believe it's a very British phrase, perhaps. Origin. And the coordinates of anything in the city is with respect to the 0 mile or with that particular origin, right? And you presume an Euclidean space. And that is what is meant. And now, what has that to do with what we are coming to? So what we are saying is, however complicated a function may be, right? The relationship between input and output may be, ultimately it is some hypersurface in the feature space. Are we together? Either it is the actual prediction surface or it is the decision boundary based on whether it's regression or classification. So do we agree to that point, guys? Simple point I'm making.
Yes.
So now, if you further impose this notion that it is smooth and differentiable and smooth and continuous and so forth, and by the way, algorithms like deep neural networks, they always produce such functions. That's what you will get by and large, right? So now comes the question. As universal approximators, they sort of do things like that. Now comes an interesting question. If you look at if you are at a point, let's say that there's a very complicated relationship. And this now goes to the point of yours. Who was asking me, Balaji? Was it you or Shiva? About the additivity.
Yeah, it was.
So let us take any point. So suppose I take this point. In one dimension, do you see that the local neighborhood of this point is a straight line? Isn't it? Would it be fair to say that? The local neighborhood is linear, isn't it? Now, generalize it to higher dimensions. So if it is a surface in high dimensions, in Rn feature space or Rd feature space, d-dimensional feature space, the local, again, the same thing happens. The local neighborhood of a point, let me take the point x naught, some point, right, x naught, and you create a local neighborhood of it, walk around it, local neighborhood will be sort of like a tangent plane, right? It's a plane, linear plane. Linear surface, right? A plane is by definition a linear surface. Would you agree? I'm just generalizing to this. So far, so good.
Yes.
Now, if that is true, let me ask this question. Suppose it is a problem of regression. What is y of x, right, in relationship to y of, if you know this, and you take some arbitrary point x in the neighborhood of x naught, or what will it be? If you do remember your Taylor's expansion, this would be, in one dimension, it would be dy dx at x naught, isn't it? Times delta x being x minus x naught, isn't it? So this is the Taylor plus higher order terms, right? This, by the way, is called the Taylor series expansion. It's something that you must have learned and have perhaps forgotten. Now I can write this equation in a form that you'll remember much more, minus y x naught. If you look at this equation divided by x minus x naught is equal to dy dx at x naught. This is practically the definition of the derivative, in the limit of x tending to, so in the limit x tends to x naught, you know that in calculus, this is practically the definition of a derivative, isn't it? And this is your Taylor's expansion. So now, this is in one dimension true, isn't it? Guys, I hope, am I saying something very obvious? Right? You have done this mathematics some point. Otherwise, take it as a fact that in the neighborhood, you are, so y of x is just the value here, plus a little bit. You take the displacement and multiply it by the gradient, by the slope.
Got it. It's a linear slope is assumed.
It's a linear slope. And now comes a question that hopefully will solve some of the riddles. So now let's generalize it to higher dimensions. Well, what it means is y of x is equal to y of x naught as a vector plus gradient of y times delta x, right? This is a generalization, and let me expand it. Y x naught plus a gradient of y, this is dy dx1 times x1 minus x naught 1, right? Plus dy, suppose there are two axes, x2 minus x2 0, 2, isn't it, guys? This is what it is, because this is nothing but x, sorry, why did I, yeah, x minus x1 minus x naught 1 I plus, if you're looking at two dimensions, if you x2 minus x naught 2 j, in terms of basic vector, you would write it like this, isn't it? And so you're just taking the dot product of the derivatives. This is the basic expansion plus higher order terms, plus higher order. So far, so good, guys?
Yes.
Just taking it. So what basically it says is that if you want to know how much y has changed, look at the change along each of the axes and add it up. Are we together? Change along each of the features and add it up. The slope along each of the features and add up the contribution from each of the features, where x1, x2 are your features in your model. Tell me, guys, if I need to repeat it, or is this clear? This is, I'm just writing out basic things here, math here. I can repeat it another way. Let me know if I should. Otherwise, I'll move ahead.
So, Ashik, y is the decision boundary and x are the features that goes and, I mean, can you explain this? I'm a little trying to wrap my head around this.
What is the question?
So the x is the what is X here? Is the feature?
It's a point in the feature space.
Okay. So you're trying to define the curve at that particular point, and it turns out to be this. Okay. Got it.
So I'm saying that in the neighborhood, if you know the value here, in the neighborhood, the value would be the value at that point plus these terms. Now, do you notice that what am I doing? These slopes are additive, right? These are the slopes, derivative with respect to each of the features. And this answers your question about additivity.
Ah.
So what does it mean? In the neighborhood of a point, locally, models are always additive.
So it's linear in the it's the hyperplane in that particular small.
Yes. So to the extent that all like functions are some manifolds, right? Some manifolds, those manifolds are smooth. I mean, assuming that they are smooth and continuous. At any point, you can do a Euclidean expansion. You can do a Taylor expansion, right? And because you can do a Taylor expansion, what will happen? Each of the gradient of each of the features will contribute in an additive manner. You see that?
Mm-hmm.
There are higher order terms. So now the problem is if you go too far from it, let's say that you have a curve like this, like this. You can't go from here to here. This is too bad, right? Because it is no more a line. So the point is, the caution that you have to take is stay local. But within a local, you are essentially guaranteed a linear model, isn't it? By construction. By the very fact of elementary calculus, you're guaranteed a linear additive model with respect to the features. So that hopefully answers your question, Balaji. Why does it?
I see. So the n-dimensional feature space, I mean, each dimension, we can just assume it to be a linear. So anything happens within that small region, it's a linear.
Yes. It's a plane. This is a plane. Or in this particular case, you notice that it is quite literally a straight line, isn't it?
Right.
Right. And so in higher dimension, generalize it, it will be a plane. And a plane, of course, a model that represents a plane is by definition an additive model. Right. Okay. And so that when you look at the contribution, and so I'm jumping ahead a little bit for your sake. When you move ahead, is it fair to have an additive model? The answer to that is yes, so long as you stay local. Right.
Okay.
That's it.
And what is the? I mean, sorry, I mean, trying to understand it from different perspective. When you say additive model, you are considering all the features independently and then working with it independently. That's what it means.
That's all it means.
Okay.
That's it.
And if that's not the case, if it's not additive, what's the problem, and when would it be a problem?
Yeah. So for example, if you say that give me global explainability, right? Give me a global explanation, then your local arguments go away. Right? See what we are explaining here. See what are these slopes? So now let's go back to something that is at the heart of today. See what is a derivative? We think of derivative geometrically as slope, as the steepness, as the gradient, isn't it? Mm-hmm. And you must have remembered that deliberately I planted ideas in your head along the way by saying that derivative is a measure of sensitivity. Right? So let me go back to that idea and I'll explain what I mean by that. See, when you say that you have a function y is equal to fx, and you make a small change in x, so x goes to x plus delta x, what happens to y? Then y would be function of x plus delta x, and that is equal to fx plus df dx. I mean, this is complete derivative. I'm used to writing it in partial form, but let me be exact here. This is in one dimension, it is this delta x. This is what it is. In other words, the delta y, so this is your y of x. So y, this is y of x plus delta x. And this is nothing but y of x. So you can say that the change of y, delta y, which is y x plus delta x minus y of x, right? By definition, this is equal to df dx delta x. Now, this is very basic calculus, but let's ponder over it and see what it means actually. So for a small change of the input, how much the output changes depends on this slope, on the derivative, isn't it? If the derivative is small, the response won't change much. Right? So for unit change in x, the response completely depends on the derivative. In fact, it is equal to the derivative, isn't it? The change in response is equal to the derivative. Are we together?
Yes.
Right?
Yes.
That is why I've often used the word, the derivative is sensitivity, and this word is at the heart of the way we'll explain things today. That it gives you how much the response or the output is sensitive to the variable x. If the slope is 0, it is completely insensitive to changes in
I
x.
see. So
Now,
if you have n dimensional, there will be n different slopes.
yes,
Each of them. Oh,
this is slope 1, this is slope 2. And so what happens? So let me ask you this question. Suppose this slope, if dy dx1 is 100 times dy dx2, if suppose this were true approximately, what does it mean? What does it really mean? For unit change along the x1 direction and unit change along x2 direction, what is y responding to more?
yeah, the 100x more on that.
100 times more of x1, isn't it? So quite literally, you're saying that maybe feature 2 is not that important locally. What matters is feature 1. Right? Are you seeing the reasoning here? By just comparing the derivatives locally, in some sense, you are saying that feature, I mean, assuming that these, I mean, there are certain basic assumptions, like assume that all the features have been standardized, normalized, and so forth. So they are on the same scale, right? But once they have been scaled and normalized and all of that, then the derivative gives you the sensitivity of the output with respect to that. So what does that mean? That feature is much more important. X1 is 100 times more important than X2 locally, right? So for example, if you would suppose it was the difference between eating and exercising, maybe X1 is the amount of food you eat and X2 is the amount of exercise you do. And you're asking this question, which will more affect the weight of a person? So today we know that eating has almost 10 times the impact or 8 times the impact than exercise. You need both to get your metabolism high with calorie intake. So for example, if you eat a big meal, 1,000 calories, you really have to run on the treadmill for a very, 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 very long time. A reasonable workout on the treadmill of half an hour is not going to burn 1,000 calories. Right? So, so you would therefore your slope, your weight change, weight will be far more sensitive to calorie intake than to calorie output that you can do through exercises. So that is what we are saying. Is the reasoning correct?
Yeah, I'm slowly getting to understand with examples you're giving. Thanks for that.
Yeah, good. Guys, the rest of you are silent. Any questions or any feedback?
Asif, the overall picture that you're describing, isn't that the basic intuition behind how gradient descent works?
A gradient descent, yes. So what it basically is, well, it sort of is there. The same calculus is behind that. In gradient descent, you don't look at the response versus input. You look at the gradient of the loss function with respect to the weights. In other words, you're saying how much is the weight change? I mean, how much is the loss sensitive to changes in the weight? Right? Similar argument, but it is weight versus loss in gradient descent. Here we are saying output versus input itself.
Okay.
That's the thing. Yeah, similar argument, but we are just changing the setting here. So this is it. So now that brings us to this question. I hope so. So guys, Now I'll explain a model. It turns out that I've already explained to you an interesting algorithm, which is called line, right? It is appropriate that I practically drew it in the color of lime, or almost, not this. Let me draw it in the color of lime just for fun. What's the color of lime? Let's see. Which would it be? This looks lime enough? Okay, let's see. Now, I screwed up. Let me have a bit of fun here. Yes. No, it didn't come through. And what then? Okay, I'm somehow not able to get lime, so I'll just stick with something. Lime. What does lime stand for? Lime stands, so what happens is, it belongs to a class of models called surrogate models. Now, we are familiar with surrogate. I very recently introduced surrogate models. Where did we talk about surrogate models? Do you guys remember?
Bayesian.
I'm sorry?
Bayesian.
Bayesian.
In Bayesian reasoning, yes. And Bayesian inference. And what was the context?
AutoML.
That's right, hyperparameter optimization. Hyperparameters, I mean, the loss is some function of the hyperparameters we don't know. And that function is unknown. So what do? We instead create another model. We use a function that we like, that we can tame, a very well tractable function, that we love. And we try to model the relationship using a function that we can understand, right? So that is what you do. So the basic idea is this. Suppose you have a black box. You treat this in line. The basic assumption is, let the algorithm be a black box, and you don't really care. Black box. What happens is X goes in, Fx comes out. Isn't it, guys? Now, Fx is rather hard or intractable in some sense. Now what you do is you instead create a model which, given X, produces G of X, where G of X is very similar to F, right? When you do that, you have created a surrogate model. You have come up with a simpler explanation of F. Now, another way of looking at it is, suppose F is like this. Well, obviously, maybe this is not quite. And suppose you come up with a model that is like this. Would you consider that this is at least a reasonable explanation, right? And at least a global explanation. Then the yellow line would be a surrogate of sorts. Now, if you notice with the surrogate, you're losing some resolution. You're losing some dynamics that's happening in the underlying function, isn't it? If you try to make a global surrogate and keep it interpretable, there's a chance that you may sort of simplify to explain what's happening. You get the flavor of this, isn't it, guys? Right. So now, the other thing you could do is, you don't need to make global surrogates. You can make local surrogates. So the idea is, suppose you make a local, right? What you do is, we did say that locally, every function is a manifold which can locally be approximated as a linear function, right? And so you can say that you will make a local interpretive. Suppose you're making it around some feature point x0 in the feature space. You make a model that's fairly accurate, but it is local, and it is model agnostic. Explanation a fancy way for writing the g of x in line. So L-I-M-E makes it line. Right? So first of all, the important word, it is local, right? And if you make a model that's sort of interpretable, what can be interpretable models? The classic is, of course, a linear. Suppose it's a regression problem. You can say linear regression. Or for classification, suppose you say logistic regression for classification. These are linear models, right? You can do that. Sometimes people find it easier to understand in terms of a decision tree. So you can use a decision tree, but don't make the decision tree very deep, shallow. Otherwise, you lose interpretability, isn't it? You need to make that if the value is more, like for example, if you have to lose only a couple of pounds, just go take a good jog or something like that. Right? If you have to lose a lot of weight, then perhaps you need to diet and exercise both. And so I'm just cooking up examples. Huh? So you can do it as a decision tree, perhaps, or as a, but make sure that the decision tree remains very simple and interpretable, right? And so locally, you want to make an interpretable model, which is agnostic to, so this is interpretable, model agnostic. What does it mean, model agnostic? So your G is an explanation, but it is model agnostic. Means it doesn't care whether this black box is what it is, whether it's a random forest or a support vector machine or a deep neural network or what it is, it absolutely doesn't matter. Right? So the heart of this goes to the fact that you have the confidence coming from mathematics that locally there, everything has a simple explanation locally or a simpler explanation locally. Are we together, guys?
Yes.
Yes. So what you do is the way Lime is done, for example, is there are a bit of technical details that I think is worth pointing out. So suppose you take a two-dimensional feature space, and let us say that you have a reference point, this. Right? So what it will do is it will do some perturbations of this data. What it will do is it will take a bell curve centered around this, and it will generate a lot of data points. So it will generate data points like this. Right? And more points closer by, hopefully. Right? So far we are clear? It will generate a lot of perturbations of the data point for which you're looking for explanations. Do we understand the word perturbation? It means vary each of the x1, x2 a little bit, go to other neighboring points in the feature space and pick those as new data points. So you generate new data in the neighborhood. And once you have done that, then what do? Then you can, in the simplest form, you can build a linear model. So suppose the decision, let me just say that this was a regression curve. Huh? Let me make it go through this. Something like this. Right? So now what you want to do is you have taken a lot of points and they are far off. You want to apply typically a weight kernel. And a weight kernel is something you would remember. We did that in a kernel KNN. Do you remember, guys? ML200, the kernel KNN, the K nearest neighbor with kernels, distance kernels, weighted kernel or distance kernels. We call them distance kernels. What does it mean? That points which are closer to this have more influence, and points that are a little bit far off, they have less influence, and points that are very far off, they have almost no influence. So in other words, each point you multiply it with some function that decays, a distance decaying function. function is called a weight kernel or a distance kernel. And so this is a minor technicality, but basically what it means is look only at the local neighborhood, and here you will have a plane. So now you can make a linear model, linear regression. You can make a linear regression model, and generally people add a regularization term also. Remember lambda as a regularization term, right? You add a regularization term. Remember lasso, ridge regression, and so forth. When it's always a good idea to regularize when you're building a linear model, isn't it? You remember that. So internally, that's all it does, right? So if you're using that, or it will build a decision tree and so forth. So this is Lime. Do we understand Lime now, guys?
So Asif, what you explained before and then this line in particular, are in the two, I mean, Lime is the particular implementation of that idea which you explained before, right?
Yes. Literally that. It is. Lime is one implementation of this idea, the basic idea, the mathematical idea. There are other implementations, but Lime is by far the most popular.
Got it. So if I understand correctly, you get the perturbations to still remain within the hyperplane.
Yes.
And then you know what kind of hyperplane it is. And
yes.
then that's it. Your job is done, basically.
That is right. That's all it is.
Got it. Okay.
Right. It's quite simple. So in other words, in the local neighborhood, you know that it will be a hyperplane. So you can make very simple models, right? Or the gist of all of this explainability using this approach is locally, everything looks simple. And if you need evidence, just think, for thousands of years, we all felt that the earth is flat because locally it looked flat, isn't it?
I'm missing some part of the intuition here. So when we look at a local area and try and understand the behavior there,
yeah,
what is the interpretation of the overall model?
No, you're not interpreting the overall model at all. You're interpreting near a point. So the whole question is, see, think of it like this. I keep going back to this diabetes thing. I'm sure that Patrick and Sukhpal, both of whom are not here today. Oh, Sukhpal, you're here. I'm sure you'll hate me for it because medically it's nonsense, isn't it? My example. But go along with it. Huh? So for a moment, so the idea is that based on what your weight is and what your age is, the recommendations would be different, right? Suppose you're in your 30s, and nowadays a lot of people in their 30s, they are developing diabetic symptoms. It's a lifestyle problem. What the recommendations that you would give is very different from diabetes in a person who's 5-year-old. 5-year-old probably means it's not because of diet and exercise. It's probably type 1 diabetes, and there's a fundamental problem with the pancreas. Right? The factors causing the diabetes are entirely different than when you see a person in the 30s. Right? So explanations differ. This is the important point, right? So what factors matter differs in different parts of the feature space. Let me give you an example. When you look at the California housing data set, housing. So you guys know that when you're looking at housing in, let's say, in a commuter city, the factor that probably matters most is not the size of, size of the house may matter, but the most important factor may be distance to the highway, because everybody will wake up in the morning and start commuting to their place of work, isn't it? So people would like to stay close to public transit and to highways, right? On the other hand, if you are looking at, $10 million mansions, for them, proximity to highway may not be a factor at all, isn't it? They're looking at entirely different factors. So when you're predicting a house price and the ranges around the, high income to very high income mansions, the factors that affect a house value are entirely different.
So Yeah, I think now I'm getting the intuition. So let me phrase it in my words. The way I would employ this kind of a thinking is to, when I try to figure out why was this house predicted at 1.3 million, right? If I try to find out why did the model peg that value for this house, at that time is where this reasoning is applicable.
You're saying that at 1.3 million, what factors affected it?
Okay, yeah.
Right. So for example, suppose you find a house for 1.3 million and you don't have 1.3 million, but you want to be there. Should you look for a smaller house? Will size bring the price down more, or will proximity to highway bring the house price down more if you're looking at other houses in the neighborhood?
Okay, so that's another entry point to the same thinking process. Yeah. Okay.
Exactly. That gives you the intuition. All right, guys. Anybody else? A lot of you are quiet. I hope you get the intuition here. That is it. And so the idea is that any local model that you build will have will ultimately have derivatives. Dy dx1, dy dx2. What are these? These are literally, in some sense, the sensitivity of the response to those features, and therefore it explains how much those features matter, right? And because it's a linear model, so for example, think of a linear model which we were used to writing as w1 x1 plus w2 x2. Now, if you take the derivative of w x1, you get w1, you get y of the x2, you get w2. You remember that, and we remember that if the data has been properly scaled, essentially it says how much y responds to changes in x1 and x2, and therefore how much locally these factors matter. They are literally given by the weights, right? And so that is line. Then comes, so this is one way of looking at it. I think it is 8:30. Guys, would you like to take a 10 minutes break before we continue on to the next one? Think and digest this. So I'll just review what I have covered. I started with a very different geometric interpretation. I said that regression and classification, ultimately, they find an embedding or a manifold in the feature space geometrically. Those things, rough intuition is they're like bed sheets. And imagine that you are a bed bug or something like that. So locally to you, the world looks flat. And if it does look flat, then locally, of course, this also goes to the heart of the fact that you can do Taylor expansions and so forth locally. So, and stick to the first order term, that's all. So if that is true, then locally you can write it in this form. If you write it in this form, you get an essentially additive model. The contributions, the change in y, or the response changes in an additive manner with respect to the two derivatives, or the feature derivatives. Right? And so locally, and because locally it's all very linear, line is putting that idea together to create a surrogate model. People often try to make a surrogate model is a model that is simpler somehow than fx, right? A gx that's simpler somehow than fx. And you can have global surrogate models, you can have local surrogate models. Line goes for a local surrogate model and interpretable, right? The whole point is interpretability here. So it makes a local interpretable explanation that gx is the explanation of fx in the neighborhood of that point x naught. And it is model agnostic. It couldn't care less whether fx is coming out of a deep neural network, it's coming out of a support vector machine, it's coming out of a random forest, what it is coming out of. There it will tell you the feature importances and so forth, and it will give you a local model. Are we together? So far, so good, guys. So yeah, one last thing I would like to do is also write the loss function. So the loss function that you say is that your gx, or your explanation, x, right? The explanation near the point x is given as is this. You look at this thing. How much does f differ from g in the neighborhood of x? Pi x is neighborhood of x, local neighborhood, of course, Implicit is built into the locality is built into the definition of neighborhood. So how much does G differ from F? Of course, for it to be a good explanation, it should closely match F, right? So for example, if you make a G that is like this, there is still a little bit of variance between F and G. And you're trying to build a model that sort of mimics or locally has a very high fidelity to F. And that's why sometimes people call it the fidelity term. I think this is called the fidelity term, I think. That's how I remember it. Okay, anyway. But then there is a problem. The more you try to make G look like F, one easy way is make a very complicated G, as complicated as F. Now you'll have a problem. G is no more interpretable. So what you do is, so this part is very straightforward. Let me just do that. You are looking for argument Gx. You're looking for that G, that explanation, the simplest explanation in the neighborhood of X, which has a high fidelity to the function F itself. And to prevent the function from getting too complex, what you do is you add a complexity term, complexity penalty term. Are we together? This penalizes the learning process if it starts getting too complicated. Now, in the case of linear model, it doesn't matter. It's not very hurtful. But in the case of a decision tree, what would it do? It would prevent the decision tree from becoming very deep or very complex. Are we together, guys? Huh? So in nutshell, mathematically, line is captured by this particular equation. Okay? Of course, and you always put it very succinctly in mathematics once you have understood it. So do we understand this equation now, guys? All we are saying is find that G, that explanation, which has high fidelity to F in the neighborhood pi of X, the neighborhood of X, right? But at the same time, you'll be penalized if you come up with a very complicated explanation, right? That is it. So come up with the simplest high fidelity explanation, right? That will explain F in the neighborhood of X. That's a summary. Okay. All right, guys. So with that summary, would you guys like to take a little break or should we just steam ahead?
I'm fine with the break.
Let's take all right, guys, and let's take a 15-minute break. After that, we have a long session. So that's why I'm giving a 15 minutes break in case you want to grab dinner or something. We'll meet after that. I'll pause the recording.
Back at 8:50, right?
Mm-hmm. Yes, let's meet at 8:50. Balaji, did this explanation come through clearly for you? I know that you
very much. Asif, actually, that's the first model I took to understand it from the paper. It took a long time. You just finished it just like that. I mean, for me, coming from it was difficult. And if this was difficult, and then there are more models, and I'm not even going there. I will wait for your explanation.
Right. No, that's the whole point, right? See, if you want to understand, I don't know, chemistry, you go to a chemist. He'll explain you simply, right? So when you want to understand mathematics, it is worthwhile coming to a mathematician.
I certainly see see it happen here. So Asif, actually, just quite interesting. So when they have this package like Shapely and things like that, they have tree explainer, they have this explainer, that explainer. So now this is a linear explainer, right? if I'm correct.
Yeah, that's right.
And if they say a tree explainer, which means they are going to use a tree-based model to explain, right? That's what
Yeah.
they are doing.
Yeah.
Okay.
So, Balaji, I'll walk you through systematically. See, the SHAP package, no? It does a lot. And to cover it fully, remember, I'll give a one-day session or an extra session at one point because it deserves that. Right. Today, I will give you a core idea of Shapely, which is independent of that package.
Got it. Got it.
That
Yes.
core idea is so powerful, it was given the Nobel Prize in 2012.
Wow.
And that's what we'll talk about in a moment. So guys, just as a warning, today will be a very long session. I hope you guys are ready to be here till 10:30. Remember, today is our last theory session. Right? And I don't know if you have realized, we have covered a lot of territory. By the time we are done, there would be 70 videos, each of them about 2.5 hours or so, 2 hours approximately, give or take, on your course portal. So I hope you will at least once review all the videos so that see, learning is cyclic. Unless you go back and review, it won't stay in your mind. How many of you remember us talking about lost landscapes and so forth?
Somewhat.
Yes. So go back and we covered a large amount of intellectual territory, guys. Much, much more than your textbook. Those of you who have read the textbook, would you agree with that? Well, nobody seems to have read the textbook. Okay. We have covered far more than the textbooks or any of the other books that are recommended. And I've taken you to the cutting edge of research. Automated ML is very, very hot. Explainable AI at this moment is at the core of research, active research. We have covered all the topics that are there in deep learning. Does anybody feel we missed a topic? No one. Good. So do review it, guys. Read the textbook and review these notes and redo the labs. Second time around, you'll remember it much more.
So Asif, since it's a break time, I just thought of asking you. So while I was playing with the Shapely package, there are many other packages as well, but they tend to not support the PyTorch. Shapely is doing it, and the transformer models and everything, they are doing it, but still they are slowly getting mature and getting there.
Mhm.
I know the fundamentals are strong, but the way they, as an end user, I'm looking at whole of my framework is in PyTorch, so I'm trying to adapt it. If I understand the basics,
To take a different approach. See, these are Shapely, line, they can be applied to any model, isn't it? So the way you have to do is literally, you have to write that extra bit of code in which you make the function make predictions and you let Shapely or line, for example, make a locally interpretable model. What you are asking for is that I shouldn't even have to do that. That's a very tiny bit of code. You can write it. That's it. So when they say that, oh, we have integrated with let's say, PyTorch or with random forest, all they're saying is, you know what, we know how to deal with the random forest as to make prediction. That's all.
Got it. I see. I think I have to dip deep into the package library to get them.
Yeah. So for example, I applied to hazard models, Cox proportional hazard model, and accelerated failure time models, Weibull and Gompertz and so forth. Right. Now, if you think about it, obviously these guys who are doing the great guys who did Shapely, they have no time to go and start supporting such small audiences like me, right? And get deep integration with this sort of esoteric models or sort of off the beaten track models that I built. I do it myself. It's just a little bit of code to integrate all that.
If I may ask, are you using the R support or the Python support? Which?
None of the above. Actually, I implemented Shapely way before SHAP package.
Oh, okay.
I literally implemented it from the ground up in
No wonder.
2012, at a time when most people had not heard of it.
That's very interesting.
We had an interesting problem to solve. I was studying, and I don't believe that any of the vendors at this moment are doing it. I asked this question. It's an interesting question that I think I answered. What makes people unhappy in the workplace, or what are the factors? So basically the happiness dynamics, right? Through some observable indicators. Observable indicators is that when you're not happy, you start showing withdrawal symptoms. Like you'll come to office a bit late, you'll want to leave a bit early. The number of email, your own frequency of outbound email goes down and so forth. And none of these factors matter, but collectively they begin to show a pattern. It's called withdrawal, right? And so you can see, another question is, what are the factors that are there? There were 200 factors. I found, for example, that how much of window, like sunlight, you get at your desk has an impact on your general sense of well-being and happiness in the office that nobody has thought about deeply enough. In fact, the only person that I know who considered this was an architect, as a brick and mortar architect, Christopher Alexander, who started this beautiful movement of, he wrote this lovely book called The Timeless Way of Living, Berkeley professor. So, and it was his work that influenced the rise of design patterns in software, that book. Right? So he used to talk about the interaction of architecture and human beings and happiness and so forth. So I borrowed a lot of ideas from such people, such philosophers and thinkers. And lo and behold, while those were things that he was saying is true, I actually proved that they are true. I saw literally the impact of these factors, but I had 200 factors that were impacting people's happiness. And the question was, how much is each factor contributing? And the results were surprising, actually. I found that money actually is not one of the strong contributors to happiness. Because within any job band, the salary band is very narrow. If you are a software engineer in a particular company, in a particular position, in a particular department, in your whole group, the band, suppose let's take a number, 150,000. The band will be between 130 and 180. Right? Does it agree with your experience, guys?
Yep, yes, yes, sir.
And so what happens is that you would imagine that the guy making 180 is the happiest compared to the guy making 130. But actually, it's not so. Money was not actually a motivator. And we also looked at how much giving more money will take away this guy's thing. And by the way, we did this research in 2012, 2013. It looked counterintuitive, actually. I repeated the study over and over again, and I went back and looked at my Shapley code. And repeatedly, it would show the same thing. So there's a little bit of an interesting thing. Using that same work, actually, shaped all of this, we started showing that people, for example, how much does, a very basic question, a guy has done a petty crime. I believe this is not being recorded, right? Yeah. So don't quote this because this is all confidential information. Or is it being recorded? Yeah. Okay. So
It's on YouTube.
it is on YouTube. Okay, let's stop that YouTube. Is it okay, guys? We'll stop that. Because these are research which are company proprietary, so I shouldn't be